There is a leaf outside your window that has been solving one of civilization's hardest problems for 3.5 billion years. It runs on sunlight. It produces no waste. It built every ecosystem on Earth. It made every breath of oxygen possible. It feeds every animal that has ever lived. And here's the part no one talks about. We didn't just copy it. In the lab, some artificial systems are already outperforming it. Almost no one knows that yet. Some hybrid systems have already exceeded crop photosynthesis efficiency under controlled lab conditions by a significant margin. Here's why that matters. The largest container ships crossing the Pacific burn up to 300 tons of fuel per day. A single crossing takes 3 weeks. International shipping accounts for roughly 3% of global greenhouse gas emissions, more than aviation. There is no practical battery system today that can power a ship like that across an ocean. Energy density isn't there, the weight doesn't work, the physics don't cooperate. The batteries required to cross the Pacific would need to occupy the cargo hold many times over, leaving no room for the cargo the ship exists to carry. Same problem with long-haul aviation. A fully loaded wide-body aircraft needs roughly 100 tons of jet fuel for a transoceanic flight. Batteries heavy enough to store that much energy would mean the plane never leaves the ground. This isn't a technology gap we haven't closed yet, it's a physics constraint, energy density. The laws of thermodynamics don't negotiate. And it's not just transport. Think about steel. The reason you can't electrify a steel mill isn't just about the energy. It's that carbon is a chemical ingredient in the process. The carbon reacts with iron ore to produce the metal. You can't simply swap it out. The carbon is part of the chemistry. Cement is even more fundamental. When you heat limestone to make cement, the rock itself releases carbon dioxide as part of the chemical reaction. It doesn't matter how you power the kiln. You could run it on pure sunshine and the carbon dioxide still comes out. It's baked in, literally. Then there's fertilizer. Most of the world's food supply depends on ammonia-based fertilizers made from natural gas. 8 billion people are fed by a process that requires fossil fuel as a raw material. This isn't a niche problem. This is a third of all the energy the world uses. And that third barely gets mentioned. They all share the same constraint. They need fuel, not electricity. Molecules. Stored, portable, combustible molecules usable anywhere on Earth, whether the sun is shining or not. Cheaper electricity doesn't solve this. It can't. We talk constantly about clean electricity. Solar, wind, batteries. And that's going well, but electricity is only part of the problem. We're not talking about your car. Electric vehicles are already solving that. We're talking about the parts of the economy that electricity can't reach. Artificial photosynthesis is the attempt to solve it, not with better batteries, not with more power lines, by doing exactly what a leaf does. Taking sunlight, water and carbon dioxide and turning them directly into fuel. That idea starts with an accident, 1967, Tokyo. A graduate student named Akira Fujishima is in a lab running experiments on a material nobody cares about. A white powder called titanium dioxide, the stuff in white paint, the stuff in your sunscreen, completely unremarkable. Then he notices something that should not be happening. He shines ultraviolet light on a titanium dioxide electrode submerged in water. Bubbles appear, oxygen on one side, hydrogen on the other. The light is splitting water molecules apart. No heat, no moving parts, no combustion. Just light hitting a white powder and producing hydrogen. The cleanest fuel in existence. It happened as if by accident, he tells his advisor. His advisor tells him to check it again. He checks it again, then again. 5 years of the same experiment, refined and rerun, every possible source of error eliminated one by one. Light hitting a white powder, hydrogen coming out of water, no heat, no electrical input beyond the light itself. He could not publish until he was certain, so he waited. In 1972, a brief paper appears in Nature, startlingly short for what it contains, and it launches one of the most ambitious scientific projects in human history. Fujishima had no idea. He was just a graduate student who noticed something strange in a tank of water. To understand why that discovery matters more today than it did in 1972, you have to understand what it was pointing at. You have to go back to the leaf. Inside every green leaf is a molecular machine called photosystem 2. At its heart, a cluster of 4 metal atoms, manganese bound with calcium and oxygen. This cluster does something extraordinary. It tears water molecules apart, 1 electron at a time. 4 steps, and it releases oxygen as exhaust. Every molecule of oxygen in the atmosphere, the air you're breathing right now, came from this reaction. Made by ancient organisms running for 2 billion years before the first animal ever existed. Think about that. Before this reaction existed, there was no free oxygen in the atmosphere. The Earth was a different planet, an alien world. Then these 4 metal atoms started running in single-celled organisms in the ancient ocean, and over 2 billion years they changed everything. Every breath ever taken by every animal that has ever lived is downstream of this one cluster of atoms. And the coal we've been burning for 2 centuries? Every joule of fossil energy on Earth is ancient photosynthesis, sunlight stored by living things hundreds of millions of years ago, left waiting in the ground. We've been burning it ever since. Here is the part that should stop you. That manganese cluster, 4 metal atoms, the same family as your batteries and the steel in bridges and buildings, has been running flawlessly in every green plant on Earth for billions of years. No synthetic chemist had managed to replicate it. The simplest, most ancient machine in biology turned out to be one of the hardest problems in chemistry. After photosystem 2 does its work, the electrons it releases travel through a chain of proteins, a molecular relay race, and that energy drives a rotating machine smaller than a wavelength of light. That machine produces the chemical fuel that powers almost every living cell on Earth. Then a second system, photosystem 1, boosts those electrons again with another photon and passes them to enzymes that pull carbon dioxide from the air and build it atom by atom into sugar. Photon to sugar. No factory, no kiln, room temperature, in water. Repairing and replicating itself using only atoms freely available in the environment. The most successful energy technology in the history of life on Earth. And yet, by the standards of engineering, spectacularly inefficient. The real-world efficiency of photosynthesis, averaged across actual crops and forests, is between 0.1% and 0.3%. Less than 1/3 of 1% of the sunlight hitting a leaf ends up stored as usable energy. The artificial systems being built in labs right now are already beating that. Natural photosynthesis in the fastest growing crops converts roughly 1% of sunlight into stored biomass. Some of the hybrid systems being built in labs have already beaten that by an order of magnitude. Under optimized conditions, yes, but the gap is real. The principle is demonstrated. The efficiency ceiling of natural photosynthesis is not a wall. What remains is turning isolated demonstrations into durable, affordable systems. So what does this actually look like? It's surprisingly simple. Just 3 pieces. First, something that absorbs light and produces electrons. Second, something that grabs those electrons and splits water. Third, something that takes what's left and assembles it into fuel. Simple as that. No combustion, no moving parts. Sunlight in, fuel out. The light absorber is what Fukushima accidentally found. The problem is titanium dioxide only responds to ultraviolet light, roughly 3 to 5% of the solar spectrum. The other 95% passes straight through it and does nothing. So for decades, researchers tried to find something better. Dozens of materials, most failed. Too unstable, too inefficient, or they dissolved in water. The field eventually converged on using 2 absorbers together, each capturing a different slice of the spectrum, like 2 stages of a turbine. But here's the thing, the light absorber isn't actually the hard part. A perfect light absorber with no catalyst is almost useless. The electrons it generates last nanoseconds. If nothing grabs them in time, the energy disappears, vanishes. As if it was never there. The hard part, the thing that stumped the field for decades, is the catalyst. Splitting water turns out to be brutally difficult chemistry. The best catalysts for decades were platinum and ruthenium, metals so rare there simply isn't enough on Earth to build a civilization-scale energy system. For years, the central question was, can you split water with something cheap, something a farmer in sub-Saharan Africa could afford? In 2008, Daniel Nasser at MIT found the answer, not just a catalyst that worked, but one that worked in ordinary water, at room temperature with no exotic conditions. Cheap enough for a single household to own, it was cobalt in a phosphate solution. A few dollars per kilogram. What his group found was almost embarrassingly simple. Cobalt dissolved in a phosphate solution was applied to an electrode. The cobalt deposited itself as a thin film, and it split water. But there is one detail about this catalyst that stops people. It repaired itself. Most catalysts, when they degrade, stay degraded. Nasser's cobalt film continuously dissolved and redeposited, healing its own defects as they formed. In a field where catalyst degradation was one of the most stubborn unsolved problems, a self-healing catalyst appeared. That paper in Science caused a sensation, not just for what it did, but for what it meant. If you could split water with cobalt and phosphate, materials so abundant they are essentially free, the cost barrier to artificial photosynthesis had just collapsed. Nasser kept going. He eventually built something he called the bionic leaf, a system that paired his water-splitting catalyst with bacteria engineered to take the hydrogen produced and convert it into liquid fuel. The artificial part split the water. The biological part made the fuel. Think about what that pairing means. The synthetic system handles the hard photochemistry, absorbing light, splitting water, and generating electrons and protons. Then it hands off to biology. Biology, which has had billions of years to optimize CO2 chemistry, takes over and builds liquid fuel, each doing what it does best, without trying to do what the other does better. In 2016, the bionic leaf reported around 10% solar to biomass efficiency in the lab. The fastest growing crops on Earth average around 1%. That is a significant improvement, even accounting for the gap between optimized lab conditions and the real world. It runs on nothing but sunlight, water, CO2, and a colony of bacteria. Nasser has been clear about where he wants this to go, not utility-scale power stations requiring billions in investment, but something much smaller, a device a single family could own and operate, a smallholder farmer in India, a household in rural Kenya. Local sunlight and local water go in, liquid fuel comes out, no grid, no supply chain, no dependence on global energy infrastructure. He has not built that product yet, but the chemistry that makes it possible exists now. That is one approach, but it is not the only one. At Berkeley, Peidong Yang's group took a completely different path. They grew forests of nanowires, structures 1,000 times thinner than a human hair, from silicon and titanium dioxide. Then they introduced bacteria directly into the nanowire forest. The bacteria colonized the wires. When light hit the nanowires and generated electrons, those electrons flowed straight into the bacteria. Synthetic and biological merged at the nanoscale. Living catalysts wired directly into a light absorber convert carbon dioxide into molecules that look increasingly like the liquid fuels already powering the world. Acetic acid and butanol are examples. These compounds could flow directly into existing engines and pipelines without modification. What Yang's work proved is you do not have to choose between synthetic materials and biology. Use each where it is strongest. Synthetic for light absorption, we can engineer properties evolution never found. Biological for carbon dioxide reduction, billions of years of optimization that we have not matched yet. And in Japan, researchers took the whole idea in a different direction entirely. What if you did not need nanowires, electrodes, or bacteria at all? In 2021, a team led by Kazunari Doman at the University of Tokyo published the largest outdoor demonstration the field had ever seen. 100 square meters of panel reactors, glass-topped trays, each one holding a 1mm layer of water over a photocatalyst sheet. No electrodes, no wiring, nothing that moves. Sunlight hit the panels, hydrogen came out, the system ran outdoors for 65 days without losing function. The paper appeared in Nature. By the standards of solar fuels research, it is almost absurdly simple. Photocatalysts sprayed onto a sheet, water, glass on top, sun above. Powder, water and light. That is it. 3 different approaches, 3 different research traditions, all converging on the same destination. At this point, the question is not whether it works, the question is why it is not everywhere. 2 problems, both are real, both are hard, but neither is a fundamental mystery, the kind of problem where you do not know if a solution is even possible. These are the problems that come after the proof of concept: durability, cost, scale. The first is stability. The chemistry of splitting water is aggressive, electrodes corrode, catalysts degrade. The best lab devices perform beautifully under controlled conditions. A commercial product needs to run for years through weather, temperature swings, impure water, and the accumulated wear of continuous outdoor operation. Progress is real. Lifetimes have extended from hours to months, but months is not years, and years is what the market requires. The second is cost. Hydrogen from natural gas costs $1 to $2 per kilogram. Green hydrogen from electrolysis runs $4 to $8 per kilogram, and falling, driven by the dramatic drop in renewable electricity costs and steadily improving electrolyzer technology. Artificial photosynthesis is currently higher still. Cost remains the central barrier. The US Department of Energy's hydrogen shot has set a target of $1 per kilogram by 2031. That is the number that makes the economics work. The price at which clean hydrogen starts competing with fossil hydrogen on pure market terms, without subsidies, without carbon pricing, on cost alone. Whether this technology hits that target this decade depends on how fast the engineering problems yield. This decade will matter, and they are yielding. Cryo-electron microscopy has now imaged the manganese cluster, the actual 4 atoms at the heart of photosystem 2, resolved atom by atom. For 50 years, researchers were working from indirect evidence, inferring the structure from the chemistry. Now they can see it directly. Those structural details are feeding into synthetic catalyst design in ways that were not possible before. If you know exactly how the natural machine works at atomic resolution, you can start engineering around its limitations rather than guessing. Machine learning is increasingly surfacing new candidate materials in days that once took years to find. The space of possible catalyst compositions is effectively infinite. No team of chemists working by hand could search it meaningfully. Algorithms can begin to. Machine learning is speeding the search. We can watch the chemistry that Fukushima accidentally glimpsed in 1972 atom by atom in real time, and use what we see to build something better. The pace of discovery is faster than it has ever been. And the history of energy technology is a history of barriers that looked permanent until they were not. Here is what success looks like. It's 2050. In the deserts, the Middle East, North Africa, the American Southwest, the Atacama, there are large installations that look like solar farms. They're producing methanol, liquid fuel, carbon neutral, made from sunlight, water and carbon dioxide pulled from the air. It loads onto the same tankers that once carried crude oil along the same routes, into the same ports. The infrastructure already exists. It just carries different cargo now. Airlines burn it, shipping companies burn it crossing the Pacific. Chemical companies use it as feedstock for plastics, pharmaceuticals and fertilizers, replacing petrochemical inputs from the other side of the world. The carbon pulled from the air to make the fuel goes back into the air when it burns and gets pulled out again in the next cycle. A solar-powered carbon loop running continuously, displacing the fossil carbon we've been accumulating since the Industrial Revolution. Now think about what that means for the industries we started with. Steel mills running on hydrogen derived from sunlight and water, no natural gas required. Cement plants feeding their own carbon dioxide emissions back into fuel synthesis. The petrochemical supply chain, plastics, pharmaceuticals, synthetic fibres, rebuilt on solar feedstocks instead of oil and gas. The sun delivers more energy to Earth's surface in roughly an hour than human civilization uses in an entire year. We have never lacked for energy. We have only ever lacked a way to store it cheaply, portably and at scale. Artificial photosynthesis is that way. And somewhere in rural sub-Saharan Africa, in rural South Asia, in places where grid infrastructure does not reach and may never reach, there are smaller systems, rooftop scale, no grid required, no supply chain required. A device the size of a refrigerator producing fuel from local sunlight and local water. No infrastructure required. Dependence on anything beyond what falls from the sky. Roughly 700 million people today have no reliable access to electricity. Not because the technology does not exist, because the system never reached them. The fossil fuel system was never going to reach them. It requires pipelines, refineries, tankers, infrastructure that concentrated energy wealth in the places that already had it. The economics of the last mile never worked. They still do not. A solar fuel system built on artificial photosynthesis does not require centralized production. It does not require global distribution. It does not require any infrastructure at all beyond a device, some water and the sun. It requires sunlight, which falls on everyone equally. That is not a secondary application. That is potentially the most important thing this technology could do. And it is built into the physics. Go back to 1967, a graduate student in Tokyo, a tank of water, a white powder, bubbles appearing where no bubbles should be. Fujishima spent 5 years making sure he was not wrong. Then he published a brief paper and started something still unfinished more than 50 years later. The molecular machines in the leaf outside your window have been running the same reaction for 3.5 billion years. They built the atmosphere. They stored the sunlight we have been burning as fossil fuels. And they do it at a fraction of the efficiency we are now in laboratories beginning to achieve. We spent 50 years learning how they work. And in the lab, under the right conditions, we have now built systems that are beginning to outperform them. The proof of concept exists. What remains is the distance between a laboratory and a factory, in a tank of water with a white powder and light. We did not just learn from the leaf, we may finally be learning how to compete with it.